Hello everyone, my name is Jialuo Chen, a PhD student at Zhejiang University. I'm glad to be here to present our work named Fast Boosting Uncertainty-Based Test Prioritization Methods for Neural Networks via Feature Selection. This work was mainly done when I was in the University of Oxford. Deep neural networks have helped us solve many real-world problems and facilitate our lives, such as object recognition. However, compared to traditional code-driven software, deep learning-based systems adopt a data-driven programming paradigm and thus introduce reliability challenges related to data faults. However, testing for DNNs generally requires massive labeled data, while building test oracles by manually labeling for a large test set can be costly. To increase the efficiency of DNN testing and reduce the labeling cost, it's essential to prioritize the test cases and identify a set of high-quality examples to review the prediction faults. A variety of test case prioritization methods have been proposed. Based on the required information, existing prioritization methods can be classified into two classes: internal-based and prediction-based or uncertainty-based. As the model prediction is based on the propagation of layer outputs, it's natural to analyze the model internal outputs to provide evidence for judging a potential prediction error. However, several studies have found that all the coverage-based criteria are not necessarily or even negatively indicative of fault-revealing capabilities. Instead of utilizing the internal outputs, uncertainty-based methods solely rely on the model's final output, that is, the probability vector. The intuition behind it is that if a DNN model is uncertain on predicting this test case, then it is more likely to be an incorrect prediction. Compared to internal-based methods, uncertainty-based methods are more lightweight and achieve better results. However, they can be further improved. Model DNN models could suffer from the overconfidence problem. They tend to give high probability scores to the wrong predictions. In such cases, uncertainty-based methods will fall short of exposing these high confidence faults. As illustrated in the left figure, uncertainty-based methods will only prioritize the test cases close to the decision boundary while neglecting the remote errors. In this work, we propose FAST, a method to improve the uncertainty-based prioritization methods to uncover more high-confidence errors. Let's start from a motivation example. Considering the fact that the final prediction results are made based on a group of extracted features, we investigate the overconfidence problem from the perspective of features. For a given class, different features have different levels of contribution to the predictions. Thus, for a selected feature layer, we calculate the feature-wise contribution for a set of high-confidence, correctly and wrongly predicted examples separately. As shown in the figure, there are clear gaps between the feature contributions for supporting the model's correct predictions, indicated by the blue color, with the lowest ranked features making the least contribution. However, these same low-contributing features could potentially yield a higher contribution towards misleading the predictions, indicated by the orange color, as they undesirably bring noisy information that is aggregated to the model's final output, further causing high-confidence errors. These features also show higher variance. Thus, we propose a simple yet effective feature selection mechanism, FAST, to selectively drop the identified noisy features, to avoid them passing information to influence the following decision process. FAST consists of two main components: feature importance measurement that quantifies the importance of each hidden feature to a specific class, and feature selection during inference, and we will obtain a new probability vector for uncertainty measurement. Specifically, the feature selection will be performed on a specific hidden layer L of the given DNN. For each class, we construct a binary feature mask M, which consists of only 1 and 0, which identifies the redundant features for each class. Specifically, The ith element in the mask equal to 0 indicates this feature is redundant and should be omitted, whereas a value of 1 indicates that the feature is important and should be preserved. Based on the originally predicted class C, the corresponding mask MC is then applied to the feature vector fx to obtain the purified feature vector. To construct the feature mask, we need to quantify the importance or contribution of each feature. The software engineering community has made a great effort to propose a variety of neuron-level metrics to guide the testing procedure of DNNs. For instance, Deep Inspect utilizes the neuron activation frequency for measuring how the neurons interact with the data from different classes. The neuron that is more frequently activated is regarded as more important. However, due to the highly nonlinear interactions of DNNs, it is still unclear how important a feature is for the model's final prediction. In this work, we conduct the testing procedure by directly assessing the individual contribution of features. Specifically, for the ith feature, we empirically calculate its contribution for a given class C by comparing the model's output difference with and without this feature, as the first equation shows. The function conf measures the model's average confidence scores over a dataset DC, and DC is a clean dataset consisting of correctly predicted examples with the ground truth label being class C. After quantifying the contribution of features, we can get a contribution vector of the features for each class. To construct the binary mask MC, we select the top k features with the lowest contribution values as redundant, setting their corresponding mask values to 0 and marking the remaining features with 1. Then we design experiments to evaluate. First, we adopt several common benchmark datasets with various different model structures. We explore first with 5 research questions. We use average percentage of fault detection (APFD) to evaluate the overall performance of a test case prioritization method, and we also use test relative coverage (TRC) to evaluate the performance of a method for a given budget. For both of the metrics, the higher the better. For the first question, we evaluate the effectiveness of FAST with representative baselines in prioritizing test cases in the clean and noisy setting respectively. The table displays the APFD values obtained by each test prioritization method, with the highest scores in bold. Across 8 out of 8 models tested, FAST achieves the highest APFD values, which is 3% higher than the uncertainty-based method, e.g. Deep Guinea. This improvement is more than 2.7 times the improvement observed with the state-of-art work NNS. This suggests the superior capability of FAST in prioritizing misclassifications compared to existing work. For the TRC values, FAST, as shown in purple lines, consistently achieves higher TRC values than all other baselines across the selection budget levels, indicating that it can expose more errors with the same budget compared to other methods. This advantage is particularly notable at small selection budgets. Thus, FAST can consistently improve the performance of uncertainty-based test case prioritization methods. To answer this question, we report the total time cost of each method for prioritizing the same test suite in the table, inclusive of any necessary preparation time. FAST, as shown in the red box, demonstrates a marked efficiency in prioritizing test input, requiring less than 2 minutes on average across various models. This efficiency is over 3 times and 9 times greater than that of other post-hoc methods, respectively. Thus, FAST is more efficient than the surprise adequacy-based methods and other post-hoc methods. To understand how FAST performs under different settings, we conduct an ablation study for FAST on 3 main influencing factors: the feature selection strategy, the feature selection rate, and the layer location. This bar figure shows the results of FAST using different feature selection strategies, such as random and activation frequency. Notably, our method, represented by orange bars, demonstrates significantly higher APFD values compared to all baseline strategies, indicating the pruned features have stronger connections with the prediction errors. Here, the line figure summarizes the trends of FAST with different selection rates. We observe that when the selection rate R is small, the APFD score increases steadily as R increases across all datasets. However, as R continues to increase, the APFD values drop significantly, suggesting a trade-off between the selection rate and the effectiveness of FAST. We further explore the impact of applying FAST to different layer locations within the model, specifically examining the shallow, middle, and deep layers. This figure shows the results. We observe that applying FAST at the deep layers consistently achieves the best performance across all datasets. Conversely, when FAST is applied to the shallow layers, it sometimes underperforms compared to the baseline without using FAST. This indicates that the feature selection in this layer sometimes hurts the model normal decision-making process for correct predictions. To investigate the scalability of FAST, we conduct validation experiments on 3 additional datasets: text, audio, and high-dimensional image. Compared to the results on image data, the improvements of FAST over uncertainty-based methods in the text and audio domains are relatively subtle. Nevertheless, FAST still demonstrates a non-trivial improvement over the uncertainty-based methods. This further validates the scalability of FAST to handle complex data and model structures. Prioritizing the test suite and selecting the valuable part to enhance the DM model performance, e.g. accuracy, by retraining is an important application scenario. To evaluate the effectiveness, we select a set of test cases with the same selection budget to retrain the models. The figure shows the performance. We can observe that FAST, as shown in orange color, consistently obtains the highest accuracy improvements across all scenarios. Compared to the random baseline, most other prioritization methods also demonstrate a certain level of effectiveness, except for the coverage-based methods. Thus, FAST can expose more hidden errors and rectify them than the baseline methods. That's all. Thanks for listening.